All right, so what I'd like to discuss with you here is how to find a function curve given what you know about its first derivative and its second derivative. Usually what I like to do in approaching these problems based on the given information, you'll notice here in these charts that we know a few things about the function itself with regards to some specific values at some specific points. We'll notice here that when x is -1, the function value is 4, so that means we have a point at -1, 4 that we can plot, which we know for sure is going to be a point on this graph. We also notice here on the function that we have a value of 8 when x is 3. So we could plot a point where x is 3 and where y is 8. So I'm going to have to extend this out a little bit here, but approximately that would be 3, 8. You'll also notice on our other chart that we have a function value of 6 where x is 1. So if I plot that point, got 1 here up at 6. We've got 3 definitive points that we know will be points on our function curve we're trying to come up with. So now we just have to determine how the function actually goes through all these points. Another thing worth noting is where the function does not exist. You'll notice on each of these charts, and this should be consistent between the two, the function does not exist at the same value of x. It does not exist at -3. So usually what this means is the value of x being -3 is undefined for the function, so we must have a vertical asymptote passing through the x-axis at -3. Another way to note that possibly would be a little hole in the graph instead of having the vertical asymptote. I just find it's a little easier, though, to include the vertical asymptote itself. Okay, after we establish some specific points and potentially some asymptotes for our function, I think the next best bet is to take this first chart and start looking at what's going on with the first derivative. We know when the first derivative is positive that the function must be going upwards. So it's increasing for the interval from -∞ to -3. If I start to sketch that in on the graph, I know my vertical asymptote's at -3. So if the graph's going to go up, basically we're going to have some sort of curve, and we could draw this a lot of different ways, but basically we're going to have some kind of curve that's going maybe upwards like so. The exact curvature of it we don't know quite yet at this point, but we do know that it's going upwards, so that would be a suitable sketch to get us started. When the first derivative is negative, we know that the graph is heading downwards. So from where x is -3 to where x is -1, that'd be from my vertical asymptote up to my first point, we know this graph has to be going downwards. So maybe it looks a little something like that. Again, right now, don't worry about the exact curvature. We're just trying to get a general idea of the direction. When the first derivative is positive, once again, graph would be increasing. So from -1 to 3, so where x is -1 right here up to the point where x is 3 right here, graph is going up, and that would make some sense because after all, these points are trending upwards. So maybe it goes through like that. And then finally we get down here to another place where the first derivative is negative. When it's negative, once again, the function is decreasing, so it's going to decrease pretty much for the rest of the graph from the point where we're at for x is 3 on. So graph might go down, something like so. So everything you see in green right now, all the green stuff is just a general sketch to give us an idea of direction. How we're going to know exactly how the graph looks is by going over here to our second chart and looking at what's going on with the second derivative. When the second derivative is positive, so here it's going to be positive on the interval from -∞ to -3. When it's positive, the function is concave up. So you'll notice with our curve that we started to draw over here, for all of our x values from -∞ up to -3 being our vertical asymptote, this curve's kind of got an idea of being concave up already. So if we accentuate that a little bit more, there's a curve that is both increasing and concave up. So we move on to the next interval. Next interval, which would be -3 to 1. So from our vertical asymptote up to where x is 1 at this point right here, we know the graph is also concave up. So in order for it to be concave up, we need to draw our curve through like so. That would be concave up. And then from that point on, from 1 to infinity, second derivative is negative. So that means the curve would be concave down. So we need to show some curvature here for the rest of the graph that's curving downwards. Well, if we have something like this, basically what we see in blue here, if I highlight all my points, and then we've got our asymptote as well, but everything in blue here would be a curve that meets the requirements we spelled out here on both of the charts. So now if we turn the page just to get a feel for another example and also get a feel for how information can be presented a little bit differently. This time it's not in a chart form, but rather we've got everything spelled out. Usually when I've got everything spelled out like this, what I like to do to get started is I like to look for what's going on with the original function. So I don't look at the f prime stuff or the f double prime stuff. I just try to highlight places where something about the original function is given. So you'll notice we've got a couple of points that are given with the original function. We know when x is -1, y has to be 4. And when x is 1, y has to be 0. So if I go through and plot those points out, I'd have a point here at -1, 4, and I'd have a point here at 1, 0. Be consistent here with the colors. Underlined it in red up there, we'll make them red down here. So that takes care of this part. I could check that off the list. And since that takes care of all the just function stuff, now let's go back and look at some first derivative stuff. Usually with the first derivative stuff, I like to look at my inequality statements. So if I notice that a first derivative is less than 0, I know for the function must be increasing. And if I notice that a first derivative is greater than 0, well, I know the function must be decreasing. Yeah, if I'm going to be honest with you at this point, I'm making this recording kind of late in the day, so I'm going to blame this on fatigue at this point, but I said that incorrectly. If the first derivative, like we have here, is less than 0, then the function is decreasing. So this is take 2, if you will. Over here, if the first derivative is greater than 0, then we're talking about a function that is increasing. I apologize for that little mistake. Hey, it happens in math, right? Now, where the function is decreasing, so if the first derivative is less than 0, it's decreasing. Here it's decreasing between -1 and 1 for x. So if this point right here represents where x is -1, and this point right here represents where x is 1, we know the graph is going downwards between those points. That would make some kind of sense since the graph's got to go through those points. And in highlighting that, filling that in on my graph, I can cross out this information now that I've used it. As far as where the graph is increasing, since I know the first derivative is positive over here, apparently it's increasing in 2 places. It's increasing when x is less than -1. So again, this is where x is -1. The graph apparently is increasing to that point. And then when x is greater than 1, so x is 1 at this point, the graph is increasing past there. So we've got our general direction highlighted here on the graph in blue, but understand, once again, that is not exactly the function we're looking for. How we're going to know exactly what these curves look like, just how much they curve, we need to now consider what's going on with our second derivative. And if you look at the second derivative, when the second derivative is less than 0, that tells me that the function is concave down. And when the second derivative is positive, like it is here when it's greater than 0, it's going to be concave up. So it's concave down when x is less than 0. So x is less than 0 would be everything, well, basically to the left here of the y-axis. It's going to be concave down, so to create that curvature, what you see there in green would be concave down. It's concave up, basically when we get past the y-axis, because past the y-axis is going to be everything that has x values that are greater than 0. It's concave up. It's got to go through, hit this point, has to be decreasing to that point, has to increase past it, but stay concave up. So if I highlight my points here in green, if I check off the remaining information I've got here, well, I've essentially used everything I need to come up with the graph of the function. Now what's interesting to note is we do have some extra information up here at the top that we didn't talk about. But understand that if you have things that relate to the derivative where we're plugging in an x value and we're getting a specific value back, in this case that value is 0. Whenever we're getting 0 back after plugging in some values to the derivative, that means we have critical numbers, in this case at -1 and 1. As far as what critical numbers help us to understand on graphs, well, one of the things critical numbers help us to understand is that we potentially have some extreme points at -1 and 1, and you'll notice at -1 we have a relative maximum, and at 1 we have a relative minimum. Now in terms of filling in any extra parts of this curve, we don't have to worry about using that information for this here. It just helps us to appreciate the kinds of points we should be seeing on the graph. So we can cross off that information. We've used all our information now, and we've come up with a graph of the function.